So, we will continue with daylighting, right, and you recollect that last class we talked about. So, there are 4 components of daylight, right, and one is the sky component, and then we said diffused externally reflected component, etc., and then we defined also daylight factors. Then we talked about the design sky, Indian design sky, etc., and then we said that design sky, Indian design sky deals with these 2 quadrants, morning, it is in the northwest quadrant, etc., and it is given like this: Bz cosec theta, right, given as a Bz is the zenith luminance, zenith brightness, and cosec theta, theta is the elevation angle, So, Bz up to this point it is Bz cosec theta, and this. Now, this is based on some of their experiments that they did, but that was pretty early, as I said. Later on, of course, new skies came through internationally, which I will discuss later on, but let us see what is there right now in the Indian code, because they thought that is the best kind of tropical sky description, right, design sky description, and that is what they have taken it. And as I said, this was pi by 12, and the illumination on a small, it is dE on a surface from any point in the sky, any small surface in the sky will be given as Bz cosec theta. Remember, we talked about Bz, this was the brightness multiplied by sin 2 theta by 2 d phi d theta. So, if it is cosec theta, simply this will be cos theta integral 0 to pi by 2, 0 to, this is not there, 0 to pi by 2 and 0 to 2 pi, and value of Bz. So, E will be given at the flat surface, unobstructed flat surface will be given as d phi d theta, which will be basically Bz 2 pi and cos theta. If I integrate, I get sin theta, right, and sin theta going from pi by 2 to 0. So, therefore, it will be pi by 2, right, simply pi by 2, sin pi by 2 is equals to 1. So, this is 1, simply this part is 1. So, Bz 2 pi is equals to E. So, they measured this illumination, and that was taken to be 8000 lux. That is taken to be 8000 lux, right, that is taken to be 8000 lux. So, 8000 lux, that is taken to be 8000 lux. In other words, you can get an idea about the Bz from this 8000 divided by, so they just obtained this, and that is what it is, right. Okay. But then today let us talk of all the tables, etc., that is there in the Indian building code, national building code SP 41. Then we will go to other kinds of sky in the next class. We will look into this. So, sky component would depend upon the area of the sky seen from the point in working plane. For example, I do not think I have the diagram right away, I will have the next diagram. For example, let us consider this is your window is something like this, right, window is somewhere here, and this is your working plane is somewhere there, this is your working plane, this is your working plane, right, this is your working plane. So, and there is okay, let us say I was talking about obstructions here, building. So, I am interested in this point to find out the illumination level or daylight factor at this point due to sky, due to the sunlight basically. So, what will happen? First of all, from this point the light will come from this zone, light will come from this zone, that is the sky component, and this portion will be externally reflected component, this portion will be externally reflected, this portion will be contributed by this, whatever brightness this has, this will contribute to this point, and this is externally reflected component as we have defined. But through this I will be able to see some portion of the sky, some area of the sky, right, some area of the sky, and that will contribute to the sky component at this point. The portion of the sky I am able to see from this point. If I place my eye here, whatever portion of the sky I am able to see, that will contribute to the sky component here, or illumination due to the sky brightness, because this will act as a source, this area will act as a source, and light will come to this point from this area only. Beyond this area it will not contribute, because nothing can be seen from at this point, nothing can be seen. So, I am dealing with one point. So, normally one can analyze point by point, one can analyze point by point. For example, you can find out in this in the room at one point, then the next point, and you can analyze point by point. But there are some way of doing gross or averaging. We will come to that sometime later on. So, one can calculate out at this point. Now, only thing now would be, area is not the full sky, not the full sky volt, same formula. So, brightness of this one is known, and dE will be simply integral 0 to or 0 or some value of theta, some value of theta depending upon what you define, 0 to some phi 1 value, and then 0 to or some angle to some some angle to some theta 1 angle to theta 2 Bz cosec theta, or whatever the Bz is, d theta d phi, right, that is what it is, into so the area would be sin theta, remember sin theta cos theta, something like this. So, this would be this would one can. So, the integration has to be performed now over the full, not over the full sky volt, but over the area for the portion of the sky seen, right. So, if you do that, then you will find out the illumination. And you want to find out the daylight factor. So, this once you integrate, you get E, and this E divided by E0 gives you daylight factor, it gives you dF, it gives you the sky component of, or sky component, sorry, this gives you the sky component, this gives you the sky component. Then you can add the externally reflected component, and because this is all linear, I mean these are scalar quantities, you can add up linear scalar quantities, you can add up. So, that is the principle, right. So, this is what is sky component would depend upon the area of the sky seen from the point onto the working plane or work plane. The area can be defined in terms of angle subtended by the opening at the point on work plane. So, it is the angle subtended, right, angle subtended. Thus, can be expressed in terms of some ratio of L by D and H by D. I will tell you what is L by D and what is H by D. L by D, L is the length of the window, D is the distance of the point, from the window at a given one corner, and H is the height of the window. So, H is the height of the window, L is the length of the window. So, H by it can be defined in this term. So, let us see what is there further. Now, this is my sky volt, this is my window. If I project it to the sky, so this is the H, this is L, this is the window somewhere in the room, and this is the point where I am interested in. This is the this, so this is this distance, we call it D, distance of one of the corner normal to the window or normal to the wall having the window to the point. So, this is, for example, if this is the window, you draw a normal to one of the corners, and it must touch the work plane. If it is not so, we know how to handle it, we will come to that. So, for calculation purpose they use this, because those days it was not hand computation, it was all hand computation. So, table generated and which are there in SP41 or the code, they are all actually hand calculation generator, or maybe small mainframe computer or something of this kind. So, this is the distance of the D is the distance of the point from the window, right, one of the corners of the window, and it has to be normal distance from one of the corners of the window, the point, but other points you will handle it in some manner. This is how so if I look at this is the area, projected area, I have made it larger, actually it is the projected area of the window, and in the sky it will take the shape like this, because sky is curved. So, if I project this window area beyond the sky vault, I mean imaginary plane, right. So, it would actually cover something of this kind, and if I project it onto the sky vault, it will be something like this, it will be a curved area. So, my integration has to be done over this area. Now, you see I can't really, variation of phi at this here and variation of phi here are not same. Variation of theta here and theta here may not be same. So, theta can be expressed as a function of phi and then you integrate it both together. So, this can be done, but they did, it in the original case they actually did it broken up into several components and did it. Today perhaps one can do numerically much easily, but this is how it was done, and the tables were arrived at, tables or paper pot diagrams, several diagrams which you find on the code or SP41, that is special publication, they were arrived at based on this. So, this is how it is. So, basically conceptually I must be able to integrate over the curved area of the sky vault, right. Now, dE is a small, I take a small elemental surface, for assuming it to be a point source, find out the illumination over the point where it is there, I mean for any point, and then integrate over this area. So, that is the idea, and this is how it looks like. This is how it looks like. This will be the kind of area, projection of the window, this length is d length, and for ease of integration what they have done is they have said that one of the, this is what is done in the code, one of the point, the working plane normal, normal to the window must be passing through the point on working plane, and this distance is d, this is h and this is L. So, the angles are functions of d, h by d and L by d. These angles are functions of h by d and L by d. Now, today one can possibly divide this into small areas and find out for each one of them numerically the contribution coming for each small area, and then sum it up to get it all. Numerical calculations could be much easier. Then they did integrate it in a very complicated manner, starting from like the relatively complicated. So, some broken up into same integration, because limits of integrations are broken up into several parts, so that this whole area can be covered. So, by doing that one could obtain the sky component. So, there are tables based on this computation, paper pot diagram, and you can do this. Today you can do computing using integration over the boundary defined by angles. So, numerical integration even you can do if required, but just numerical integration may not be necessary, only limits are problematic thing. Limits are not, the two limits are there. So, as distance changes theta, as distance changes phi changes, but theta also changes with phi. So, accordingly you can do the integration, right. Okay. I don't go into details of these integrations at the moment, because this itself is in question. The design sky, it needs relook. Some relook has been done. So, integration part is fairly simple, but since it is there already in our design code, I would like to explain this first, then introduce to you the other kind of skies that is possible, and possibly way how you can do it if you want to do it that way. Many software uses those skies, but then you have to be careful to choose the correct sky for Indian condition, or for given place in India. So, that's all, or given place elsewhere in the world. So, this itself is in question, therefore, there is no point spending more time on integration, but whatever is there in the code I would like to cover. So, tables are what I will be discussing. How tables are pretty simple to use. Now, these tables are, as I said, h by d and L by d. So, for example, h by d 0.1, L by d 0.1, h by d 0.1, the daylight factor in percentage chi component is 0.036. Now, how do you find out L by D and H by D? Let us see. So, this is kind of a table is there, large table is there. So, from this table first you find out L by D and H by D. In order to do that, the one assumption is made that the working plane point P and normal to the window from one of the corner must pass through P. So, this is your L, this is your H and this is D. So, L by, so if your working plane is such that it passes through this, then there is no problem, straightforward you can use. But supposing your point is somewhere here, the window is something like this. So, according to this assumption, the normal from from this point, if I draw a normal to the wall or the window, it touches the window at this point. So, I divide this into two parts. So, L1 is this, L2 is this, H is common and D is this distance. So, what I do? I find out the sky component for L1 by D and H by D, and also I find out sky component for L2 by D and H by D, then sum it up. So, then I am not violating this principle that normal to the normal passing through the work plane or the point in concern touching one of the corners of the window. Here it is touching the corner of this window and here it is touching the corner of this window. So, you can use the L by D and H by D table and sum it up. If your point is somewhere here and window is ABCD, in all this diagram window is ABCD. If window is ABCD, then this will not contribute anything to the sky component. Why? Because window, your point work plane is above. So, it only comes from the top, from the bottom the ground does not contribute here. So, what you do is you again find out for this portion of the window and this portion of the window and sum it up. So, what it would be, say this is L1, this is L2 and this total is H and this is let us say H1. So, you will find out for L1 by H minus H1 and L2 by H minus H1 and sum it up, and that is how the tables are used. That is how tables are used. The only thing is you must ensure that the point of concern, normal drawn through the point of concern, must pass through one of the corners of the window. It could be right corner or left corner, does not matter. So, more general case is let us say something like this. Now, this is your window, this is your window ABCD, it is somewhat below. So, now what you do? You consider this L by D for this one and L by D for this one, sum it up and subtract the L by D for this portion and L by D, L by D and H by D for this portion. Okay, let me just write it rather in a more clear manner, so that it becomes clear. So, for example, for this case I first find out the sky component for N F C M plus sky component for N E D M minus sky component for N F B L minus sky component for N L AE. First I find out for this portion full and also find out for this portion full amount, full quantity. Then I find out for this portion which I subtract and then this portion I subtract. So, then that would contribute to the sum total of this one, because I am not violating the principle for this one. I am not violating the principle that one of the corner of the window. So, hypothetically I can assume the window is of the larger size, then subtract for this portion, which is again I am not violating that one of the normal drawn at the window, one of the corner at the window passes through the work plane. So, this is how we can find out. Now, this is still more general. I suppose this must be there here, not really, no, it is not there. So, let us take it this still more general. ABCD is my window, right, this is my window and my work plane is point of interest is here. So, what I do? I draw a normal passing from the point touching the wall which touching the wall is this, then I extend this to at the up to the window end, extend this up to the window height, and this is my L1, this is my H1, let us say. For this I can find out the sky component, right. Then what you do? Find out the sky component for this portion, and then find out the sky component for this portion. So, what we will do? First you have found out for the total, total everything. Now you have found out from this, for this. So, subtract this. So, what I have done in the process, I have subtracted this one twice, add it up. So, sky component for ABCD would be SC for ABCD in this case would be SC for NFCM, I just extend this, and if it's plus minus minus NL, SC for NL BF minus SC for NEDM, right, and then I got to add, because I have subtracted this twice, SC for NEAL. That will give me the sky component for this. So, for corresponding L by D, H by D you can find out, and then find out from the table, and then. So, this is how one can use the table, right. This is how one can use the table. Similarly, for this also you can find out. So, this is more general, most general. So, all you do is extend the as if hypothetical window size to match that condition, that normal drawn at one of the corner of the window must pass through the point of my concern. So, every point you can calculate this out, that means in other words you can analyze the sky component values everywhere, right. So, that is what current code as it exists does. So, that is what I was saying. To find for this, you have to first find for this first, find out for this, subtract, and this you add again. So, that is how it is done, right. So, that is how we can use the table. Similarly, there are some other diagrams I have provided, but I think it is not worthwhile anymore, because tables are good enough if you want to use this same table. But today you can yourself do some simple integration. If you understand the basics, then you can yourself write a program and do the integration. But the sky itself is in question. Similarly, for projections outside, you have to find out the shaded portion. If there is a projection, for example, you have a crate shading device. So, that would actually block some portion of the sky. So, all the visible sky portion you will take, and accordingly you can find out, right. So, this is what our code does. Let us look at externally reflected component. Now, externally reflected component, what would change? The brightness would now change. So, brightness will be the brightness of the external obstruction, either the tree or the building or whatever it is, right. So, we define something called sky factor. Now, what is sky factor? Sky factor basically sky factor is defined as illumination due to externally reflected components divided by brightness. Illumination due to externally reflected component at that point by sky brightness. In other words, what it is, first thing we do is we assume that brightness of the obstruction is constant. So, we assume brightness of the obstruction or building is constant. And we are in the code writes it in LOBS. Actually, we have been using B, but since in the code it is also used, the notation used is L, I have kept it same as code, so that you refer to SP41, you will find that it writes LOBS. So this is what is assumed. Then supposing now my obstruction is, I know the obstruction area. For example, I was just telling you earlier that this is my room, the window is somewhere here, right, and the building is somewhere there, building is somewhere there. This is my working plane, this is my working plane, this is my working plane, and this is my point. So this portion will contribute to externally reflected component, right? And therefore, again this has got a something like this. So that there is an area involved. This is the obstruction area, because the window width is also there. So accordingly, there is an area involved which has got a constant brightness. So how do I find out the illumination due to this? It will be simply the brightness LOBS multiplied by sin 2 theta by 2 d theta d phi, and the integration will, limits of integration will depend upon the size of the obstruction. It will depend upon the projection of the obstruction onto the window. It will depend upon the projection of the. Now you see, LOBS is constant, so I can take it out. So this, so this will be what? This will be, if I integrate from appropriate angles, appropriate limits, phi 1 to phi 2 and theta 1 to theta 2, if I integrate it, this gives me simply ERC, illumination due to ERC, isn't it? Illumination due to ERC. Illumination due to ERC, because integrated from theta 1 to theta 2, phi 1 to phi 2, this will give me the illumination due to the externally reflected component, right. Now therefore, since LOBS is constant, I take it out. So ERC divided by LOBS, that is nothing but that integration part, integration sin 2 theta, which is actually, again I can write it in terms of L by D and H by D in the same principle. So this is called sky factor. So sky factor is nothing but ERC divided by LOBS, which is nothing but, just let me erase this out and just. So what I am saying is sky factor is ERC by LOBS, because this was expressed in percentage. So ERC by LOBS, if it is expressed in percentage, it will be like this. This is nothing but, this is actually integration theta 1 to theta 2, phi 1 to phi 2, sin 2 theta by 2 d theta d phi, right? Am I right? This is right, because this is what we saw for a small element in the sky, 2 sin theta cos, sin theta cos theta d theta d phi was there. So I have just written it in this manner. So this is nothing but multiplied by 100 anyway, if I leave it 100, because LOBS if you take. Now this I can find out for various L by D and H by D. Like earlier I did the integration with Bz cosec theta, but now I will not do Bz cosec theta, I will do it for just no Bz, nothing, just this part. So this is what is sky factor. This is what is sky factor. Similarly, sky factor tables are given in the code. Sky factor tables are given in the code. So sky factor, if you find out, and it's the same principle, one of the corner must pass through the one of the corners of the window must pass through the normal to the point, same principle as I just discussed earlier. Now there is no problem with this. This is absolutely fine, because this has nothing to do with the sky. Only thing here you need is LOBS obstruction of the external ones, which are taken for different surfaces. If it is direct sunlit surface or diffuse sunlit surface, facing the sun or not facing the sun, building, etc., bright, whitewashed and so on. So it will depend upon those kind of scenario, and we assume it to be constant. So, sky factor tables are not, it's not, it's not dependent on the sky type. It's not, so these are usable even today, and exactly in the same manner we use them in the same manner as I just mentioned earlier. So, ERC can be then obtained because sky factor you can determine from table multiplied by L obvious, which is given again in a table. I will just tell you something related to this table, and E0 is 8000 lux is given. E0 I told you already 8000 lux for the kind design sky that they have. So, externally reflected component of the daylight factor you can actually find it out. So, this is a principle actually, this is a principle. So, we will break and again start from there, right. So, whatever we will discuss about the types of obstruction, right. So, we will just break. If you have some question I will answer in the meantime.